Start her up. Hello everyone, welcome to the live stream. I'm here with Russ with RWG. Hopefully isn't it? So today I have a special treat because Russ is with me, and yeah, in case you don't know Russ, maybe I'll have him explain who he is, what he does.
I'm a dude on this planet, and yeah, I do alternative energy research related projects most of the time. Autofocus just happened. That's going to probably happen a lot.
Yeah.
But hey, yeah, I'm basically just out there in the world trying to experience what's possible and what's not, and I do a lot of that. Looking at it from a quantum physics sort of point of view, where I go down to the bottom level and look up and start from the ground and go that way instead of using our known laws in physics per se, and try to make something with it. So I always basically ask the question,
Yeah.
what can you really do? So anyway, that's kind of my background. Got a couple of degrees in robotics and industrial maintenance is kind of where I started, but most of what I do is self-taught. Try to do everything open source, sharing with the world and giving back, and yeah, just being faithful and sharing my faith along the way. And it's actually one of the main reasons I do what I do is because yeah, I believe a strong faith. Christianity is my background. And I believe a strong faith is very important to achieve these kind of goals. And I don't know what else I can say about myself. I'm just a guy doing a thing, trying to be helpful. And, you know, I don't claim to know anything, but I'm an expert at nothing, but I can do about anything. Put my foot in there and get my hands dirty, and I'm willing to have some fun along the way. So anyway, that's kind of, I don't know what else I can say at the moment. That's my background. Strong faith.
Yeah, no, that's great. That's great. You're just a dude doing a thing.
I'm a dude doing a thing. You know, we all got things to do, and I'm just doing my thing, which is sharing, caring, loving, and expressing and having some fun. And also, I guess, real quick, if you want to know more about me, you can go to my website, which is rwgresearch.com, or open-source-energy.org is the forums that I technically own, but everyone else really keeps it alive and keeps it going.
Yeah.
And yeah, you can check those two things out. You can also just Google my name, which is Russ Gries. You'll find my YouTube channel on my website and everything. And yeah, recently I haven't posted a whole lot on there, but try to do at least a weekly video, sometimes twice a week. Recently it's been a little slow, just too many projects and not enough focus on one to really make any good sort of content out of it. So one day at a time, as I say.
Yeah. Yeah, I know how that goes when you have multiple things going on. It can be a challenge for sure.
Yeah. Yeah, it's good. It's all good, but yeah, it's just sometimes I want to make content a lot once a week. I try to get at least once a week on a consistent schedule for the viewers so that they kind of know when content's coming, because I think that's important. But what I learned though is that I've tried to make my channel great and make it expand and have lots of people, you know, join this channel. And I've had the channel since 2006. What is that, 12 years now?
Yeah.
No, 13 years now. It's a lot. Yeah. It's a long time.
It's been a while.
Just very slowly climbing. And I went through a lot of trial and error and tried to like do amazing things and it really didn't take off. And then I did like random stuff and it took off. And like,
That's
what
the
am I
way it
doing?
goes.
Like, what's going on here? So I learned basically you can't please anyone and make what you enjoy. So I just
Agreed.
post what I think is entertaining, what I think is interesting, what I think is helpful. I still try to do my series that I call The Search for Answers, which is basically me expressing what I understand, what I know, and kind of how I've learned what I've learned in the field of energy research. Autofocus all the way, boys. Anyway,
Yeah,
it's
man.
terrible.
No,
But,
that's good.
anyway,
Yeah, you
yeah,
threw a little.
that's a long intro.
No, it's not intro. You just gotta describe yourself to people who don't know, right? Even though,
I am a guy in a green shirt with a hat.
Yeah.
Now I have no hat.
Yeah.
I have a hat.
and we both have that in common too. We're both.
We both got big ears. You just can't
Yeah.
see mine as much.
Mine are a little more Shrek'd out than yours, I think.
But when I was a kid, though, I had bigger ears and I was much shorter, so I looked pretty hilarious.
Yeah, well, it's a way to stand out from the crowd, like Dumbo. Total placement here. It's coming out soon into theaters, so
Yeah, Dumbo is?
yeah, they're doing a live action Dumbo, and
Really?
you know who they're replacing the mouse with?
Who's that?
Danny DeVito. Makes perfect sense, right?
Really?
You don't seem too impressed.
That's interesting. I don't watch much video.
Yeah.
Much. I watch a lot of YouTube and people I enjoy watching on there, but I don't do any. I either am building something, blowing something up, or watching a YouTube video and
Learning
try to fit
something.
my family and my wife in there, which is they should be priority, but it's hard some days.
Yeah.
Now, they
Yeah.
are priority, but it's really hard some days. Focus
Yeah.
on them.
The work-life balance thing is a challenge, for sure.
It's not easy, but what I've learned is just no risk, no reward. But I look at it as a little different motto, which is you can't get comfortable. You got to stick yourself out there in the unknown, and you'll do great things.
I agree.
Because things will develop for you if you are able to just be faithful. And that's the way I've lived my life. And I tell you what, it's been a blessing and an amazing adventure so far. And Lord only knows what's next. So we'll see.
That's the excitement of it, right? I completely relate to that, totally. Yeah, I'm in the same boat right now with several different things, and kind of similar to you, although I haven't been able to do any of the hardware type research. I've been missing that, but I'm kind of limited to my space and everything, so. But
yeah.
I completely relate. So what's the project you're working on the most right now? Are you able? Is it hush hush? Are you able to say it?
No, I mean so I work on a lot of different projects, and some of them for the guy I work for, and so it's not my project per se. But a lot of the stuff I can talk about. Only a few things I can't. That is basically just not mine, which is like any other job in the world. If you work at a company that has proprietary information, then you're under the same agreement as I am with any other thing I do. But basically, yeah. Recently, I've been building this plasma chamber thing, and I can't pronounce these people's names at all. But it's a plasma device that these guys developed back in 1995. If you just Google pulsed abnormal glow discharge, you'll probably find it.
Does it need to be a Google scholarly article, or?
Actually, there's a patent. Let me.
Yeah, you sent me that. I have it somewhere on my computer, but.
Yeah, I actually have never seen a patent written this way in my life. So I'll give you the patent number here and pull it up, because it's actually pretty interesting that that this patent is written in such a way where it's actually like a research article.
Yeah, when I was looking at it, yeah, it's very.
It's very strange. So it's strange as in you normally just don't see that. So the patent number is US 5449989. 5449989. So maybe you can pronounce their names better.
I'll do my best.
But basically, yeah, this device is
Citations.
it's been out for a very long time, And I don't know where it went. I don't know what happened to it, but the details are so thorough that like you almost can't deny it. Now, some people believe that these individuals are a bit kooky, and I personally believe that they probably stumbled across something, researched it, studied it, published it in an article format, and then put it into a patent as an article format. So there's a couple of them. This is the one. You can look up the rest of their names for the others.
Oh, it's
But
not in there.
basically, this is so detailed that you can build the entire
There we go.
thing with just the 2 or 3 patents that they've published. It's pretty incredible. All the
September
data's in there, all
12th,
the information's in there.
Yeah,
Um,
Korea or Korea. I mean, I don't
I
know.
can't pronounce their names, so that's
Yeah,
why I don't even try.
they're like, they must be related, or they.
Yeah, they're husband wife actually.
Oh, okay. Wow, that's pretty cool.
Yeah, it is.
So on the cathode of an arc drawn in a vacuum. So they're
Yeah,
establishing a vacuum arc, and
yeah.
you've been
Well,
experimenting with this, right?
yeah. So pull up the schematic,
All right.
and I'll kind of explain it real quick. So I'm actually looking at.
If it lets me here.
Yeah, it will. Just
Oh,
scroll
I gotta
down
scroll.
the
There we go.
pad.
Start with this
So
one.
basically, you have a battery, and then you have a ballasting resistor and a couple of diodes. The battery's high voltage; it's between 3 and 600 volts, and it's basically the same thing as a ballast system on a fluorescent tube. So you basically have a high current at the beginning, and then you stop the current with the ballasting. In this case, it's just a resistor to limit the current. And then you have a anode cathode plate. These things are huge. They're very large, up to 256 square centimeters is what they use. Pretty big. And um, and then
Any
you have two coupling capacitors there, and then that goes into a recovery circuit. So you got a full wave bridge, and that dumps back into a charge pack, what they call a charge pack. CP and DP stands for drain pack, I believe it is. So you got a charge pack and a drain pack. So what they've discovered is that you basically allow the plasma to form, and then you cut it off right before it creates an arc. And so that you do that by the ballasting resistor there. So the thing surges, but then all of a sudden gets restricted, and then you collapse the plasma, and it does it again. It actually pulses anywhere from 2 to 10,000 pulses per minute. It goes, it's all kinds of different um, pulse rates depending on the plate and the gas and the vacuum and the system, the setup, the batteries, the voltage, everything.
right.
Here. But basically, in my opinion, what it does is it expands a few free electrons from the aluminum and vaporizes the aluminum in some cases very slowly, and it'll actually release those few free electrons, and then it'll collapse. And when it collapses, you can capture those free electrons. So I believe that's uh, what's probably happening here. To be totally honest,
So like an electron water hammer in a sense, right?
yeah, exactly.
Yeah.
So a long time ago, probably a year and a half ago, I explained this electron water hammer idea in one of my the search for answer videos,
Mm-hmm.
and this actually applies almost exactly in that thought process. So this relates, in my opinion, to Edwin Gray and his plasma discharge tube. Um, it relies on the avalanche, electron avalanche. So you create these free electrons and then you capture them in your circuit. And it's totally known science. It's not impossible. It's really hard to actually capture those and put them into your circuit. Normally what happens is they get dissipated as heat.
Right.
In my case, these electrodes got super hot on my last couple of runs. So you can only run it for 5-10 minutes, and then you got to let it cool off because I don't have any external cooling or anything. But yeah, it's interesting. I honestly have no idea what. I haven't seen any results yet, but I knew it's a fine tuning thing, and so I done burned out a few diodes here and there and found that out when after I did a lot of testing. So I got to go back and do a lot of testing again, and different vacuums, different gases. I'm using argon.
Okay. It's very
They
that's
used
pretty conductive.
they used argon,
Okay.
and then they used air. Those are the primary gases. Now, there's a gentleman named um, oh, I'll think of his name here in a minute. George Eagly.
Yeah,
And
I know him well.
So George, I met George at a conference in Italy once. Amazing guy. And he basically studied this for about 10 years. And he said that, or his opinion is that it's some sort of a plasma ball lightning effect. And if they would have used, let's say, deuterium, which would probably cause lots of radiation and X-rays potentially. So, but if you're doing transmutation and stuff, if you set this configuration up using deuterium, you might come up with a completely different result. So if anyone ever follows that path, be super careful. That's dangerous stuff.
Right.
I've got a Geiger counter and a neutron detector and an X-ray detector all set up in case anything would happen here in my lab, so I didn't kill myself.
Are you picking up any like X-ray emissions or anything like that?
No. And see, the voltages here are less than 1,000 most of the time.
Okay, good.
And so you're almost completely out of that range. Now, if you pulled a super hard vacuum, which I can't achieve a super hard vacuum, like an ultra high vacuum, if I could get to that point, you potentially could generate some X-rays, but I can't get to that point. So I have not seen anything bad come out of it. I also haven't seen any positive results yet, but I'm still messing with it. I really just started, and I haven't worked on it as much as I would like to. But yeah, that's actually a project I'm working on now, and that came about through actually working on some Edwin Gray stuff. I haven't really published any videos on that. You'll see some random stuff here and there. My primary focus is working on Joseph Newman's work. So
you still have those huge coils for that too? You still working?
Yeah. Yeah, this room here, I used to do everything in this room, and then finally got the garage set up, which is my current laboratory. This is like the clean room. I sit in here and do programming or drawing in CAD, and then I'll print stuff out with the printers and the coil makers and stuff back here. But everything's in the other shop, so you can't see it in here. But yeah, I do, and I learned a lot from that. And I think there's something there that I would say Newman ran across, found, discovered, didn't fully understand, but his theory of magnetism, his theory of everything, basically of magnetism, quantum field theory of magnetism, is genius. It's great. It's amazing.
Simplified.
It probably describes everything perfectly, or extremely close to what's actually going on the microscopic scale without actually knowing what's going on down there. But using his understanding, he discovered a principle that seemed to work, and he followed that path. He knew he had to build it big. He knew he had to do certain things, and he did it. And I personally believe that he had something that probably worked, but he didn't fully understand it. So when he built his new iterations, he was trying to find these things that weren't fully there. Because I haven't actually seen any positive results with anything I've tested so far. But I've learned a lot. I've learned a lot to get me to a point where I'm thinking very critically about certain things. And that's why I built what I call the cheesy fan.
Right.
And why is it called the cheesy fan? Because, well, I printed it with orange plastic. I put holes in it to save plastic, and it looked like a chunk of cheese. So it became the cheesy fan. So anyway, so that's very important for me, because that's actually what I've been primarily focusing on for about 1.5 years now. And I still think there's some merit to that. I still think there's some something interesting there that should be followed up on. I actually, one of my friends, Richard, has kindly donated a lot of magnet wire, magnets. I've got the shaft to build a 2 foot long, no, 2 foot. Actually, it's about 1.5 foot wide by 28 inches long motor with 200 pounds of number 30. It's all here. And what I did is I built the cheesy fan, which helped me understand a few critical points, which I still have to go and do some more testing on. That's a never-ending test platform that I built, which is great, except it's a lot of work. There's 200 individual wires, and every time you want to change something, you have to reconnect all of them. And
that's why you built the cheesy fan, right?
That is the cheesy fan.
Oh yeah.
So the cheesy fan uses flat pancake coils, which I can kind of show you right here what one of these flat pancake coils look like. So this is kind of a test piece here. But this is 30 gauge wire, bifilar connected wire, and yeah, I built 50 of these coils. My goal was to make 100, but 50 was all I could get with all the configuration I had. I couldn't get the tape off like I wanted, and I had to use extra thick film, so I lost a lot of space.
And for those that don't know, like you have a 3D printer like attachment, and that's what you're using to make those, right? You have a whole video on it and everything, right?
Yeah, there's a whole entire video series on that, and it's a pretty sweet deal. I got a lot of publicity for that. Here's an example of one of these coils that I can make. You can actually see it's almost completely transparent.
Yeah, it's beautiful.
So this is actually 47.5 gauge, and printed it right there on that machine. Right, I can't get my finger to bend that way. This one right here.
You got it.
So a finger won't bend the right way. But anyway, this is the kind of coils I was making, and actually a lot of other people have a lot of use for these. So if anyone wants me to make coils, you can. You'll have to pay for them, of course. I can't do everything for free, but I'd love to make coils for people, because the system I built is pretty. It's actually not complicated per se, but I spent probably 3 months just dedicated time on getting it to run as cleanly and as nicely as I have, and learned a bunch of ways not to make coils and how to make coils.
That's usually how it goes.
My goal is to make specific geometries and very tight corners and even squares and all kinds of things. And I pretty well got to the point where I was satisfied. And then now it's like, it comes down to almost a material science. What kind of tape do you have? What kind of adhesive does it have on it? How thick is it? What wire diameter? And all those parameters change with wire diameter, and what roller width, and how programming, and it's really complicated at that point. But the basic of making coils, especially just spiral flat coils, is perfect. Now, on the Cheesy Fan, those coils are bifilar, because I wanted to add capacitance into my system. I can explain to you what I'm trying to do there, which I haven't really made a video about. But basically, if you look at inductive reactance and capacitive reactance, okay, and you determine where the counter motive force is. So you've got, EMF, electromotive force, and then you have CEMF, counter motive force. That doesn't sound happy. But basically, when you draw those out on a graph and you look at how those things are set up, you start to realize that if you had an opportunity to run a coil as a capacitor and use its magnetic field, then you have a completely different scenario. And so the goal for that particular system, my Cheesy Fan, is to understand how far I can take that with generic coils and wire without going to some sort of high, I don't know, some other platform of doing the same thing. So those coils are bifilar, and I connect them in such a way to add extra capacitance, and then I've stacked them so I can have even more capacitance, and I end up with a very complex but very diverse system where I can connect this thing in all kinds of different ways. I can get down to 0.2 ohms, or I can have up to 820 ohms just by configuring the coils in certain ways. And I can change those capacitances, I can change those inductances, and it's a model for what I wanted to build the big one as. The 28-inch, by 1.5 foot coil that's got 200 plus pounds of wire on it.
Yeah.
Before I wrapped that wire and then decided I wanted to do something different, I built the Cheesy Fan to demonstrate these principles. But if you just look at the EMF and counter EMF and you ask how you can apply counter EMF with EMF, you can actually resolve the equal and opposite reaction using that methodology. And it's something that I would like to make a video about, but haven't really put everything together in a way where I'm super satisfied. And so once I'm satisfied with my deep thoughts there, then I'll make another the search for answer videos, and I'll continue down the path. But
now, have you noticed like a decrease? Because this is something that Tesla obviously experimented on, is bifilar coils, right? And their capacitance, their higher capacitance value, and their help with the counter EMF. Have you noticed a decrease in magnetic field when you're using it, like with the cheesy fan motor, for example, or?
No, see, you gotta put a few things together. One of those things is what Newman tried to teach us, which is you can create a magnetic field that's astronomically large with almost no input. Well, how do you do that? Well, you remove the heat dissipating factor. You basically have a high resistance coil that has a lot of turns. When I say a lot, those big coils I got, they weigh 135, 145. The one weighs 215 pounds right now, and it's got over 170,000 turns on it. So when you do the equation of turn counts, right, amp turns, you realize that you can put in just a few milliamps of current and produce the same magnetic field as if you expended 50 amps.
It's just at a higher voltage, though, right?
It's at a higher voltage.
Yeah.
But the wattage is only like a few watts. Where if you go the other route, all that current gets dissipated as heat, and it's just wasted as heat. So it's an IR square loss problem. That's one example of why Newman did what he did, is he got rid of those losses altogether. I mean, what you put in is what you get out, magnetic versus electric.
Right.
Almost exactly. There are almost no losses in that system when you look at it from an IR square loss situation. Even though it's high resistance, you actually lose less because you don't heat the wire up. You use that current to your potential, to your benefit. So that's a very important part. I didn't answer your question exactly, but that's a super important part of why these high turn count, low current coils are important.
Right.
Your question specifically, ask me it again.
Are you saying that Joseph Newman was using a bifilar coil? He's basically using a bifilar coil?
So, he did connect some like that, because there's actually a few drawings on a whiteboard in the video where he's actually shown that. But I don't think he thought about it that way.
Okay.
So he was just connecting things in certain ways that made sense to him, but I don't think he really understood the capacitive component to this, the dielectric component to this, the electric field component of this. I don't think he fully understood that, and I say that because if you just watch all of the videos all the way up until the day he passed away, you start to see that he finally starts realizing that that's a critical piece. He says certain words like this, add enough capacitance to where when you switch the commutator, the spark goes away. Well, what are you doing? Well, you're tuning the system to create a system where you're actually switching on the peak of the wave. So, and why do I know that? Well, if the current is moving up and you pull the plug, you have a humongous arc. But if you wait till the top and then you pull the plug, you won't get a spark because the current's at a state that's not changing, basically, right? As long as the current's not changing, you won't get a spark. But if current is flowing, current is changing, current is moving, then you'll get a spark. So it's on the peak of the wave where it's starting to come back down. And he says stuff like that, and you go, oh, he doesn't describe it as a tuning parameter in a way that I would look at it, like where you got to equal the capacitance to the inductance, right? The cheesy fan I want to run at its self-resonant frequency. But why would you want to do that? If someone would ask, well, I want to do that because that's exactly where the inductance and capacitance balance out.
Right.
And that's the most important part of what I'm trying to do.
That's like any motor. I mean, if anybody who study electrical engineering, that's you have to do that with the motor. That's why they add, capacitors to a lot of motors and stuff like that for the power factor correction. So yeah, I mean, makes sense to me.
Yeah, and I actually want to go in the other direction. I actually want to go all the way positive 90. So instead of just stopping at the self-resonant frequency, I want to go all the way to where it hits 90-degree phase shift. And that's because if you draw out the current and the voltage at that phase shift, you look at the counter EMF, you find out where it's at, you realize, in my opinion, that when you get to that point, if you're using the magnetic component of a capacitor, you're playing in a new field that most people don't play with because you normally can't get there. So if you engineer to get there, which is what the cheesy fan's supposed to do, and it does, but it's still not at the frequency at the frequency I want. For example, Newman's coils, the one I built, the one that Richard, my good friend Richard, wrapped by hand, has a self-resonant frequency of 120 hertz. That's unheard of. Like they're normally in the terahertz, you know, a megahertz range. This is 120 hertz. So I want to, and Newman operated in these rotational frequencies of that frequency, and so I believe that if you build it big enough and you have enough capacitance, you have enough inductance, you can play in the field that I want to try to play in, and it's hard to get there with a small amount of wire.
Right.
So
you know, what frequency range were you saying now? I missed that part.
Those big coils.
Yeah, they'd be lower, right? Like
they operate all the way down to 120 hertz. That one.
Yeah. Okay.
By itself. So that's super low.
Yeah.
Now, if you ask what rotational frequency that is, it's something on the order of 6,000, I think. So if you want to match the RPM of your rotor with the frequency, like I'm trying to do with the Cheesy fan, you still got to go at pretty high pretty high RPM still.
Yeah.
But you build the thing 3 feet diameter, 4 feet diameter, like Newman did, then you have another scenario where it drops even lower, even lower than that. And there's a lot of evidence. If you look in Joseph's book, I happen to have one. This is the long story. I need to make a video about this, but this is the book. And what's funny about this book is my friend bought it and gave it to me, and I realized it came from the library of the university that I went to college at.
That's funny.
and he bought it for like $10. These books are going for a couple $100 easy. The guy didn't know what he had, and he just sold it. So anyway, but in the other edition, the 8th edition, you can look in the back of that book, and there's a lot of letters. It might be in that one too, but by the way, that's a PDF online. If you just look for the 8th edition, The Energy Machine of Joseph Newman, you'll find the PDF. And there's a letter in there by Dr. Roger Hastings, and he specifically says that his motors operate around the self-resonant frequency. You kind of start putting it all together, and you hear what Newman said about tuning, and you hear about what Dr. Roger Hastings said, which is like the only guy who really spent hours and days with him.
Right.
With Newman.
There's quite a few people that came out and tested it too.
There is. There's over 30 affidavits of signed people, even from NASA and all sorts of places, that agree that the measurements are accurate and the device produces excess energy. And it's funny, if you do the math, this is written in the book, if you do the math for back EMF versus turn count versus your current going in, you get up to about 100,000 turns or so, and you actually cross a path where you'll get more you'll get basically more back EMF, right, out of the system than you put into the system using known math. So, hey, I'm on the phone right now, okay? So, come sit down then. This is my daughter, Riley. But, so basically, it's actually using known math of the current type right now. Just go get any math book and just write up the equations. You'll find out that they cross somewhere, and then it's like, oh, so you mean using known physics and known math, you can actually get to a point where you can get more back EMF than you put in. It's like, really? But you ever built a coil with 100,000 turns? It's not easy.
Yeah. I mean, and it's almost in a sense like, I don't know. What do you think as far as the science behind that principle? Like, if it was to work, like, what would be the science behind the principle? Why would more mass equate to more energy back out, or energy back, I should say?
Yeah. Well, Newman claims that he was turning mass into energy. So if you think about it, your copper. This is kind of Newman's words in my own perspective. But the copper is actually already got the magnetic component in it. And what you're doing is you're just exciting it. So you can literally excite what's already in the copper just by putting a tiny bit of current in there. And when you get to a certain turn count, you get to a certain point where you're actually putting out a magnetic field that has an electric component to it. And the electric component, at that level, when you get to some certain voltages, you actually start getting not necessarily a corona field, but you start getting free electrons in the system, and I believe you can actually capture those free electrons. So literally turning mass into energy by extracting electrons from the copper. And let's say you're not turning the mass into electric. Maybe you're just pushing the electrons out, then capturing them. And of course, they're going to balance back out, right? They're going to replenish themselves from the natural environment around you. So, that's pretty straightforward. That you could do that.
There's a tough question, like, because in quantum physics, like the common understanding of electrons, from what I've ascertained, right, from learning, is that electrons actually, they don't move; they just basically interact with one another, right?
Yeah. So people talk about electrons moving in a wire, and actually, it's the drift velocity. It's super slow. It's terribly slow. So, you're actually I can't really go into it in detail in a way that would make logical sense here, because I think of it in my own way. But can you leave the door open? Thanks. So basically, the drift velocity is super slow, and if you take a coaxial cable and you ping it, basically you send a signal down it, you can actually measure like 100-meter length, and you can determine what the velocity of the electron movement really is. It's super slow, so you can kind of put that into perspective. Some people are like, is the electron even real? It's actually an electron cloud. It's actually blah blah blah.
Yeah. Well, I mean, yeah, it's still it's a subatomic particle, so right, so it's still very much mired in quantum physics and theory, like many super large things and super small things are, they're out of our true, like, visible range. All we can do is conceptualize it and stuff like that. So yeah, I understand what you're saying.
Yeah, it's really it's you can look at it in a bunch of different ways. I really enjoy looking at the magnetism component, as spin, and how, and this is what Newman's theory really discusses, and how that really works. Why is it at 90 degrees? Well, if you take a gyroscope and you twist it this way while it's spinning, it wants to go that way, and you do it the other way and it wants to go the other way, and then you move it directly in the same direction as its axis and it doesn't do anything.
Right.
And like, you can apply those principles directly to understanding the electric field, what we call in the older days, now I like it still, the dielectric field, right?
Yeah.
And the magnetic field, and you can put these two together and you can find out, well, these are all 90 degrees from each other. So when you're creating magnetism, in this case with a coil that acts more like a capacitor than it does a coil, an inductor, then you find out that actually those things are at a different direction. Those 90-degree angles are now in a way where they can actually aid you in this. And in Newman's work, geometry plays a critical role here. The coil's inside, or the magnet's inside the coil in a way where it never passes outside of the coil. And if you do the experiment, you can find out that the current that you put through it and the direction that the magnet wants to spin, when you hook up the right polarities, you'll find out that the induced current from the magnet is in the same direction as the wire. So in that retrospect, you find out that the direction of the magnet spinning inside the coil, inducing a current, is in the same direction as your applied current. So the question becomes, can you induce more than you're applying? And then you get into like pulse cap discharge type of work, and you realize maybe you can actually instantaneously pulse that coil super fast and then recover all that inducted
current
induction from the magnet, in the
current, in the true sense of current,
wanting to go in that direction already. Like, it's like I said, when you really study what he did and how he did it, you start to realize that there's like a bunch of different things that make perfect logical sense, that get you to a point where you start thinking about this in a way that I think about it, and then you build something like the cheesy fan. And then, because that's 2 pounds worth of wire to do the same thing that I've had to expend, I don't know, 80 pounds worth of wire.
Right.
And so just on a regular spool, because you're engineering exactly what you want to see in this case. So anyway, so yeah, those are some of my
Now, did
thoughts on that.
he didn't open source a lot of his stuff though? It didn't come to light until like later on, right?
Well, he wrote a book, right? And almost everything that he learned is in that book. There's a few things he claimed he learns towards the end of his life, which is what I'm explaining to you right now, that the capacitive component is critical. So I see you pulled up the PDF. There's two PDFs out there. One is a picture of the actual book, and one is text that's been like converted over. I highly recommend you read the one that has the photographs. If you look for them, it's kind of hard to read on certain pages, but it's better in my opinion. Whatever floats your boat.
Yeah.
But yeah. So the capacitive component is the thing that I don't think he ever really talked about in the light that anyone just reading is going to understand, unless you dive in and actually build and understand why he did what he did. Then you go, oh, like I did. Oh, okay. Now I see why he said certain things about adding capacitors was helpful. But if you can build it in, it's even better.
Build it into the actual coil, you mean? Is that what you're suggesting? Yeah.
Exactly. That's what the cheesy fan represents, is a coil that acts more like a capacitor at the right frequency.
So this goes back to the original question, which is, have you noticed a difference in a bifilar coil's ability to create working force, like in a rotor? Like, is it greater or less, or do you notice a difference, like compared to just a single wound coil with the perspective, counter,
right?
Yeah, electromotive force compared to like a bifilar one? Do you notice a difference?
Well, I guess you'd have to apply that question to the right test. And so in my testing, tested a lot of different things. I've tested open-ended coils, closed coils, coils that go in and then back out, then back in, all kinds of different configurations. And depending on what you're trying to do, it changes the magnetic component. Yeah, absolutely. But the question I think you're asking is it more beneficial only in the right scenario? So I've not seen any extra magnetic field or something like this.
Yeah.
Right? But what I have seen is the coil acts completely different, because you're changing the phase angle at which the current voltage wants to move by creating a coil that acts more like a capacitor. I mean, it's a very different way of doing things, and depending on what you're wanting to do.
That's such an engineering answer to say. How dare you?
I mean, I got the cheesy fan to test the principle of running exactly how I wanted to run, and it only does that really well. I mean, it does a good job at what I wanted it to do, but if you try to hook it up some other way, it's just a normal. Might as well just wrap the wire around it normally, right?
Yeah.
It was a huge effort to build what I build, but the effort was worth it for what I was trying to test. So
it basically halves the windings too, right? So, does it decrease the power consumption at all? Does it add because there's a counter motive force, or there's a counter electrical force? Does it make even more resistance? Does it increase the resistance, or does it actually pull more current?
It's an interesting question. So if you run a coil like a capacitor, and you do what I tried to do, you actually start running into a scenario where you create more capacitive reactance to a point where you're actually creating more resistance that's actually there. But if you balance it right, you can actually find out that you can change it in such a way that it actually helps you. So, for instance, on the oscilloscope, we're testing, me and Richard was here helping me for a while, and me and Richard are trying some things, and we look at the curve, right? The curve of the trace, and you look at it and you go, I just applied voltage to a coil, and yet the curve was actually a capacitive charge curve. And you go, well, that's not right. No matter how big or small, you would expect to see an inductive charge curve with an inductor.
Right.
And in this case, we saw a capacitive charge curve at the right, with connection.
Right.
Which really like throws you for a loop because you're literally charging that coil like a capacitor, but using the magnetic component. That's just.
Is it with a plateau and everything? Like it has a plateau and.
Yeah.
Huh. And so you can measure
pull the wires off, and you can discharge it. It's like what? But again, that
makes sense.
That's the design of the coil that I wanted, right?
Yeah. No, it's almost like a holistic way to build a coil. Yeah.
But to answer your question, in that configuration, it actually wasted more energy than it was helpful.
Yeah. See, that was my question, because if you have this counter electromotive force, or this counter force in the coil, like I would think that would be, even more resistant in a sense, or it'd take more power. It would require more power, right?
Yeah, like for instance, if you actually leave the wires open, like a capacitor, and then you try to charge that thing up and use the magnetic field isn't very big because you only get whatever current went in there as a displacement current. And the displacement current sometimes is actually a lot smaller than the conduction current that you conventionally see. But what's important there is that you can now extract that energy back out. So, like, I had a question, can I charge that thing up literally like a capacitor, use the magnetic field, and then recover all that energy? Because, see, this whole principle of operation is energy recovery. So, in that setting, the magnetic field was terrible because you charged like a capacitor. So, the current, if you look at the curve, the current is not what you think it is, and so it levels off real fast because the capacitance is pretty small in that configuration.
Right.
But let me explain this to you. So again, these are things I'm trying to make videos of, but just haven't been able to get around to it. But you can watch the live stream recordings, by the way, by looking up on the open-source-energy.org. If you look up the Newman thread and go towards the end, you'll find I posted all the live streams there. You can go back and watch them if you're real interested. Because I haven't had time to sit down and make these. But one of the things I did, make these videos, one of the things I did was I wanted to know if you could take a capacitor, run it through a coil into another capacitor, and use the current that you're moving through the coil, but recovering in another capacitor, right? So it's energy recovery. And what I did is, originally I took a 500 microfarad cap, and I ran the cheesy fan for as long as it would run with the coil and the cap, and it would run for about 7 minutes. That's the best efficiency I could get, which is still pretty good for a 500 microfarad cap. And that's charged from 100 volts down to about 20 volts. Okay, so remember those numbers. 100 volts to 20 volts. And the length of time was 7 minutes. Okay, now I took a coil cap configuration and I went from a capacitor to a coil to a capacitor. Okay, and so I ran the current through the coil and recovered it. When you do that, you can actually transfer all the energy from one to the next. But the capacitor I had on this side was really small. It was only like 20 microfarad. But I had two of them in parallel. So what I did is connected two of them in parallel, and I took 100 volts from this cap and charged up these caps to, let's say 98 volts or whatever it was. Then I took while running the motor, right, the cheesy fan.
Right.
And then I connected these two capacitors from parallel to series and shot it back into the 500 microfarad caps, because I went from 98 volts on the two caps to almost 200 volts. It dumped back into this other capacitor that was now at a lower value, right?
Right.
Now, when you switch these, you actually realize that the joules is very important, because you go from parallel to series, you lose like a lot of your joules of energy there. But what you also realize is that you don't lose your dipole. So you go from 100 volts to 98 volts back to almost 200 volts, and then back to the 100 volt cap, and you can transfer that energy back and forth. The only loss that you get is the resistance of the wire in that case.
And so if it's all done in the coil itself, it could be beneficial, is what you're trying to kind of experiment with.
Well, so what I wanted to know is, can you recover energy from one place to the other while moving it? Can you use it? And since my motor is inducing a current in the same direction it's flowing, it's actually helping it move. Okay? So in that configuration, right, parallel series, dump, dump, parallel series, dump, back and forth.
Right.
I got the motor to run on a 500 microfarad cap for 14 minutes. Now you go 14 minutes, that's like exactly double. It is, and here's the interesting part. Instead of from 100 volts to 28 volts, it went from 100 volts to only 50. So my efficiency just went up 4 times by doing that.
Yeah.
And the motor still ran just as it did before. Now I couldn't quantify torque, or I didn't include RPM. What I included was how long can I run this system on 500 microfarads. So the efficiency still might only be 50%. But I went from, let's pretend if it was, I went from 25 to 50 or
right.
75 or whatever.
Well, and you can still with your time variable and RPM. So how many times it rotates per that time? Yeah. You can still get your calculations. I mean, even though you're not, seeing the amount. I mean, that's what a motor is really for.
Yeah.
For work, right? But
yeah, and there's a fan on there. It's moving air at a rate that you can feel with your hand, so it's doing a little work. But it's interesting because just by trying to capture energy and not dissipate it as heat, right, from a coil straight into or from a capacitor straight into the coil, and just waste it as heat, right? I actually just transferred it back and forth and used that current as it flowed through the wire to do work.
Right.
Now I can tell you that in that configuration, if I were to hold the motor in a standstill and do the same test, nothing changes. So the fact that it's rotating or the fact that it's not rotating, there's no change there in the amount of time that takes to dissipate the energy through the resistor, basically. I did that test several times through many different test configurations and realized that in that geometry, in that configuration, the induced current and the counter motive force from the induced current, which normally impedes it gives you cogging effects and problems like this Lenz's law and all this stuff.
Right, exactly.
You actually find that in the right configuration, you can eliminate almost all of those problems, and you can get a system to run super efficient.
And that's really what it's about, right? Is trying to
because
the efficiency, right? Bring up the efficiency.
Right, and here's a question for you: if I pushed you, right? If I stood you up right here and I just pushed you as hard as I could, half of my push went into you and half of it pushed me backwards. Right? Yeah. If we were the same weight, of course.
Right.
So in this case, electromagnetics is exactly the same. You push forward, but half of it pushed backwards. The half push backwards is what you see on your shaft in your generator in this case. As a generator, it's right. You see that going back. That's your counter motive force.
Right.
So if I asked a simple question, which was, well, what if I could remove the counter motive force and just either eliminate it altogether, or actually create something that would aid the system? So instead of me pushing you and you going one way and me going the other, we'd both go the same direction, and that same amount of push would equate to twice as much work.
Right.
If that could be done, then guess what?
Yeah. Just put you up against the wall.
Well, exactly, but then you're still pushing on the wall,
Yeah, that's true. That's true.
In a different way.
Then you're just ringing. You're ringing between me and the wall, right?
Yeah, exactly. But the question there is, if efficiency is calculated as an equal opposite reaction in magnetism as a 100% efficient system, right? Then by applying that simple thought, you could automatically jump straight to 200, right? 200%. It's a plausible.
Theoretically,
yeah.
Right? Yeah.
Yeah. Well, if you just look at counter EMF and EMF, and you draw it out, and you run things in the right way, and induce currents in the same direction, and you apply all those principles, which is basically what Newman's work taught me personally, then you realize that in the right configuration, under the right circumstances, you can actually probably do that, which is what I've been trying to prove. And for me, I have to get down to the self-resonant frequency of the coil in the RPM range, and I haven't been able to do that with this small coil. I did it once with the big coil. And in my opinion, if you have an equal opposite reaction, then what you put in is half of it's going to push back. But if you get at the self-resonant frequency, then you won't have any of that. If you get above the self-resonant frequency where you're in a capacitive operation, then actually it should help you. It should aid in your rotation. And I've proved that principle on the bench once before the coil shorted out during that test. And so I know that that's the right way of thinking about it. Now
that was the big coil, right? The big coil shorted out?
Yeah.
How did that make you feel?
It made me feel very unsatisfied.
Yeah. Did you take it apart? Did you take the coil apart and find where it shorted or anything?
170,000 turns on it.
I know.
To do that. No, I know exactly where it shorted. It shorted somewhere between the first winding and the second.
Yeah, well, that's... I can see that'd be a bummer.
The coil's still usable in certain circumstances, but I can't run the test that I ran like that.
Right, because of the voltages.
So it's unfortunate. It shorts it out. It shorts
the coil out. So
I was using the individual coils as capacitors, right?
Yeah.
And when I got up to about 2,000 volts, well, it shorted out.
Yeah.
But it's interesting that I got to that point, and that's the only time I've seen it in person on my bench where I could go, this is the right way of thinking. Now, how do I engineer it? And that's where the cheesy fan came from. So the cheesy fan came from that thought. And now I know I can get the self-resonant frequency lower, but once you connect the coils in a certain configuration, you actually add more resistance than there is in the system, which is obviously very bad.
Right.
So you have to stick with a certain coil pattern and configuration, and in order to do that, you still got to go with a pretty big coil. So yeah, I'm looking right here. I've got Richard basically donated the wire and the magnet. I've got the shaft here. He donated that as well. Put the bearings on it. It's all here, and now it's okay. Before I waste $2,000 worth of 30 gauge wire, how can I build this exactly the way I want it?
Right.
So, and that's why the cheesy fan came about, is to answer the questions that it's now answered. And so now it's finding the time and possibly building a machine 4 foot by 4 foot to actually wrap these coils by filer on a flat plane like I've done in the cheesy fan, which is, it's crazy to think about that.
Very complex. Yeah.
It's not something, it's like, and then you ask the question, well, if it only gets you to 99.8% efficiency, if that's the case, it's not worth the engineering effort. But if it could push you past 100 by using just known laws of physics,
like a COP of 1, you mean?
Yeah, if you're just achieving a COP of 1, then that's great. But if you spent 6 months and $30,000 in one motor, then nobody's going to buy that. Nobody's going to use that. Nobody's going to build that.
It's not cost effective. Exactly.
No, and that's why we still have the same boring technology that we got.
So this is a beautiful segue too. It's a beautiful segue. So your concept of free energy, like what do you think of that, using that term free energy? What's your take on that?
When people ask me what I do, I tell them I work on alternative energy, and they go, well, what kind? And I said, if you've heard of it, then it's not what I do. And because we work in an alternative energy field that is going to achieve something that some scientists say is impossible. So I personally don't usually use the term free energy because I believe that every system is an open system. So free energy is something I don't usually use. I usually just use alternative energy. I believe whatever energy that is quote unquote free is just the environment around you. If you can put heat back into a block and you can steal the heat from it all day to make a motor run, then it's technically free energy. But I don't know why I don't like that term.
Yeah.
I like energy from the environment or something along.
It's more along the lines of thermodynamics. If you put it in that, if you say it's alternative energy to what we currently use, right? I mean, like, I've always been the same kind of way, like the term free energy, because immediately people say, oh, you can never get anything for free or whatever, but then it almost, to me, falls back into like, well, that's kind of how we've engineered things to be, right? I mean, so...
Solar panels is exactly the definition of free energy.
But it's not, because we have to spend the time and effort to build them and yada, yada, yada.
But at some point, you're going to reach a COP of 1.
If you take care of them.
If you expend 50,000 watts to make a solar panel, and you let it run long enough, and it expends more than that amount of wattage, then you've just achieved the COP of over 1.
Right,
and that's an impossible thing to do. Well, no,
right.
Just using the environment around you. So wind is a really easy one. Right? I mean, stick your foot out, your face out there, and throw some grass in the air. I mean, you didn't pay for that grass to be blown across the yard.
Yeah, or even like a passive solar system is a great example too, with the use of heat.
Yeah, so when people say there's no such thing as free energy, it's like, well, actually,
yeah,
world revolves on free energy.
It literally does.
The sun keeps us alive.
It literally does.
For that, I mean, ultimately, my faith teaches that someone else sacrificed for that one, But,
right.
But yeah. So anyway.
Yeah, it shows it's a blessing. It's a gift, our most precious gift. So.
Yeah, and I think if you don't ask why, if you just stick with the scientific facts that someone hands you and you don't ask why, then you will never achieve something of which I'm trying to achieve, because you're stuck with engineering facts. And
right.
I am on a deep level quantum physics sort of thinking, where it's all unknown.
Right.
It's all
and pushing the boundaries, and also that brings me, because I know we got just a few more minutes, but there's an Instagram post that I put up of something that a bit about, and I've dabbled in, but it has to do with bismuth, right? And cooking the bismuth, and they're turned into like a big question on it. So you can see the screen, right?
Yeah.
All right. So this particular post, people were talking about how this is like fake because he pulls such a big bismuth crystal out, and I just want your take on this. You can see it, all right?
Yeah, it's loading because I'm watching it through the other thing that's coming up. So, it hasn't loaded yet. Hold on. There we go. Oh. Okay, I haven't actually seen that. Yeah, that's a big crystal.
You've seen this. You've seen this video. What's your take on this video?
I don't think I've seen this one actually, but I'm watching it now on your screen. So, bismuth is an interesting thing. In a pot that big with that much bismuth, if you cool it right, yeah, you can make that.
Yeah. How do you think he does it though? You think he's heating the perimeter of it, like to slow heat?
I don't know, but I know for a fact it's a critical temperature mass here. So bismuth, you cannot make bismuth crystals like that unless you are at the exact critical temperature, and you basically are removing the crystal as soon as it starts
forming.
Yeah, it's forming, and then what is liquid will run off. Because if you cut a crystal open and you were to look at the structure and not damage it, you'd actually find out that all that is in one giant chunk.
Right.
So if you do what he just did, that's a humongous.
That's impressive too, that he got the critical temperature so accurate, right?
I bet he tried that more than a few times.
Yes, that's what I said.
I've tried making these, and it's at the right temperature. No, I think that's achievable. But you gotta hit that exact temperature, because what's happening here is usually it solidifies from the outside in. Or
right.
It goes
solid
from the
exactly.
outside in.
Right.
But in this case, if he had a crystal and he stuck it in there cold, it would start growing around it, just like a sugar crystal on a.
So you think he was seeding? You think he was seeding the bismuth? Okay, okay, that's a good idea.
I don't think he'd be able to do that.
So, and then there's one more question that people always ask is, why is the level of the bismuth not going down as he's lifting it out?
I'll have to watch it. Let's see.
It goes down ever so slightly, but not very much. Considering.
How big that pan is.
Yeah, I don't know how deep it is.
Look, you can see the surface tension of the. Oh yeah, it's going down. You can see the surface tension of the bismuth, like solidifying on the top.
Right.
And as he pulls it out.
And that's usually how it goes. Is it kind of solidifies on the top first, right? Because that's where it's cool.
Down.
Ever so slightly.
It's not as much as I would think, but there's probably some. There's probably the bismuth seed looked almost like it's got some hollow spots in it. So there's a lot of internal structure that's not solid there.
Yeah, that's a good point too. There's
a lot of internal structure that's probably not solid. You can see there's a lot of voids and holes, but you just can't see through them. Actually, you can see through them in that one spot.
Yeah.
I don't know. It definitely went down. You can see it. See the side of the pan?
Yeah, it went down a little bit. Yeah, it's just the questions that people ask.
You know what, Dylan? If someone donates some bismuth, I'll make one.
Test it.
I need a lot. That's probably
You want to make your levitators.
So I make levitators and I sell them on my website just for science, purposes for people to just see how cool that is. And I don't have that much bismuth.
That's expensive.
That's probably oh man, that's probably a good 150 pounds worth of bismuth.
It's expensive. Bismuth is heavy too. It's not a light element at all.
Yeah. Okay.
Well, cool, man.
Fair game. Someone says send me 100 pounds. I'm on it. I'll do it.
Yeah, right.
I got this.
Sounds good.
I'll try my best anyway. All right. Well, thanks for the call here.
Yeah. Thanks for coming on.
Hopefully people get some interest. I've never really sat down and explained this thought publicly to this scale, so I'm going to send people here whenever they want to, find out a little bit more about
what you're working on
are currently. And that's, today's date is what? April 4th, 2019?
Yeah, the 9th. Today's the 9th.
April 9th, 2019. So, a month from now, my thoughts will gain.
Your birthday's coming up soon too, isn't it?
Yeah.
Yeah. Don't think I don't forget about that stuff.
Well, you shouldn't forget about it. If you put 2 and 2 together, everyone knows. Like, nobody seems to figure it out. I think it's quite funny.
Yeah, well.
I'll let that hang. Somebody will figure it out.
Yeah. Well, cool, man.
Awesome.
I appreciate you coming on. It's always a pleasure chatting with you. It's cool getting some of your thoughts on to the interwebs. Without grinding or robotic motions in the background and drilling and so.
Hey man, you gotta do what you gotta do. Right?
Yeah, I know how it goes. I know exactly how it goes. So, and if like I said, if anybody's interested, Russ does tons of open source stuff, and he always has cameras on. I mean, almost always, not always, but most of the time he's got a live stream going, and you can kind of see what he's up to. And check his channel out, RWG Research. He's got a lot of great videos, that's for sure. Very informational.
Yep, that's what I try to do. Share love, care, teach, learn.
And I was going to do a video or a giveaway, but we only have like 2 people on here, so I don't really know how that's going to work out.
Well, you guys are going to have to come back if you
want
to.
I'll have to do it, attempt it next time. And I have a little spinner widget I want to use on this and test these out.
Sweet.
Look, I got stuff like this too. Woo! You'll see that in a second, probably. There's a delay.
Yeah,
but yeah. But cool. Anyways, thank you so much for watching, guys, and thank you, Russ. And until next time, enjoy every moment to the present.
Peace out.